Good afternoon, everybody, and thank you for coming. I have to admit, this is really awesome to see this many people coming out to see one of our great space activities at 2 o'clock in the afternoon on Thursday. I mean, you guys give yourselves a round of applause here, because this is pretty incredible that we got this many space people at AWS reInvent. So thank you all for coming. You know, I wanted to talk to you guys about introducing this session. This week, AWS announced several blogs, really cool customer testimonials, and all showing how they were using AWS services to support space exploration, decision-making, and generally helping to make the Earth a more secure place. Ultimately, you know, the true value of data that we collect in space comes from turning that information into something that can be used to help improve life on Earth. And so today's talk with Tim and Kate is really designed to show you guys how regular people, regular businesses with AWS services can build a complete space business. And to really drive this home, in 2017, I had just come to AWS. I've now been here for 5.5 years. And I was at a conference for all of us space people called the Space Symposium in Colorado Springs. And in 2017, I was talking to the founder, one of the founders of HawkEye 360, and nothing had been put up in orbit. Now it's 2022, and we've actually got a whole constellation of HawkEye 360 satellites that are orbiting the Earth, collecting data and doing good things for the world, and processing that information on AWS. So I just wanted to get into, I'm not going to give you any spoilers, because that would be just foul. They've put together a really great presentation for you. But at a high level, they're now going to discuss how you can build a constellation of spacecraft so that you can collect specific types of data from around the world, and then you can actually bring that data into the cloud, analyze that data using machine learning and building models so that you can apply AI to it and make inferences and actually find things, detect problems, and actually identify issues to the world so that you can actually move in and save the world, defend our environment, and make sure that everybody's following the law. So over to Tim and Katie. I really am happy to see you guys here, and take care, and thank you for coming to AWS reInvent.
Thank you, Sean.
If we could see radio waves with the naked eye, we'd learn a lot about how we communicate, navigate, and lead our daily lives. But until recently, we've been unable to study this marker of modern life. At HawkEye 360, we're transforming this unique resource into a new layer of knowledge. Through our pioneering radio frequency analytics, we geolocate or pinpoint radio frequency emissions to illuminate global activity. It starts with our clusters of small satellites flying in triangular formations in low Earth orbit. With satellites, we can detect radio frequency emissions with an incredibly wide field of view, day or night, in any type of weather. Based on customer needs, we tune the software-defined radios to selected radio frequencies in our growing library of signals of interest. As a cluster passes over an area, each satellite observes the signal waveforms. Our satellites then downlink this signal data to a secure cloud environment, where our proprietary algorithms compare the waveform data of all 3 satellites. We look at tiny differences in waveform properties to confidently geolocate individual signal emissions, and then package signal characteristics and data for rapid delivery to customers. Our customers use this first-of-its-kind geospatial intelligence to reveal what was previously unseen, such as vessels trying to hide, changes in patterns and behavior, and new activity where none should exist. Our customers deepen situational awareness by leveraging our RF analytics to tip and cue other sources as part of a fused multi-intelligence solution. As our constellation continues to grow, revisit rates will drop to about half an hour. To give our customers unprecedented access into a new dimension of knowledge, that will help them make decisions for a safer world.
Welcome. We're very excited to do this talk today, Kate and I. HawkEye's been working on, as you heard, collecting space data for about 3 years now. You may recall the SpaceX launch where both the rockets came down simultaneously. That's when we launched our first cluster. You see from the agenda here, we're going to talk about maritime domain awareness, talk about how we collect data, and then Kate's going to talk about the specifics of how we get valuable information on that data. What you see here, and it was mentioned in the video as well, is that we fly in formation. What that means is we have clusters of 3 that we launch up into space, and they travel in formation. And when we collect the data, they have 3 different looks at the ground. So that's the way that we use triangulation to find the location of emitters on the ground. This is a shot of our data over the last year. The different colors indicate the different kinds of emitters that we can geolocate. So the blue is AIS. We collect AIS, although there are people that do that for a living, so it's not one of our main signals. But you can see that when collected over time, cumulatively, you can begin to see things like shipping patterns. In North America, you see pink emitters, and those are push-to-talk radios, land radios. We have push-to-talk marine radios as well, and satellite phones. You'll also see you'll see orange, which is marine navigation radar. So any vessel of any size has radar, and it's how they navigate and how they see other vessels. A vessel of a certain size is required to run AIS, but occasionally, for whatever reason, the AIS is not beaming, but they're always running their radar, and we can see that. As you know, we're a satellite vendor, so we have 5 clusters of satellites in the air now, and they're circumnavigating the globe, kind of like the International Space Station. Every 90 minutes, they loop the globe. You see other satellites here that can collect data. You also can get data from airborne sensors, so it's drones or airplanes or those kinds of things. And then you have terrestrial sensors as well. So some of the AIS vendors collect data satellite. They have terrestrial sensors, and then they also have sensors on vessels. So this is just a variety of ways that remote sensing platforms can collect data. So this video shows you the footprint that we can collect as we circumnavigate the globe. And it builds and it shows you cluster by cluster. As you add another cluster, you get more visibility. And right now we're at 5 clusters. So think 5 clusters of 3, and it's a cluster's going around, another cluster's going around, another one's going around. And right now we're at about an hour and change in terms of revisit. So every spot on the globe, we can see within an hour or so, we're back there and we can see what's down there. And this shows you just the kind of coverage that we have as we deploy those 5 clusters. We're going to go up to at least 10 and potentially 20 clusters, and with a final revisit rate of 20 minutes. What that means is that we'll have one satellite that comes over that spot every 20 minutes. Won't be the same cluster, won't be the same set of satellites, but we'll have coverage when we deploy the full constellation. So right now we're at 5 clusters, or 5 times 3, 15 satellites. The way that we collect, on the bottom, what you see is the radio frequency spectrum. So it goes from, on the bottom with the big waves, about 150 megahertz, and on the top end, it's 18 gigahertz. So that's the entire radio frequency spectrum of which we're capable of collecting. And you see it's noted clusters 5 through 8, can see most of it. There's a couple little gaps there. And then what we do is we roll out new clusters. We're always upgrading our antenna, upgrading our firmware, and things of that nature. And so we'll have coverage of the entire radio frequency spectrum. Now, on a given collection, you have to choose a chunk of the swath to look at. And you see those lines there. So you kind of pick UHF, VHF, maybe mobile sat phones, maybe marine navigation radar. But we are capable of collecting anywhere up and down that spectrum. Here what you see are different kinds of use cases. You say, okay, you can see all these radio emitters on the ground. What are you looking for? All right? So if I look in the far left, you see illegal fishing. So although vessels may turn off their AIS beacon, an AIS is a beacon that think every 6 seconds it says who I am and where I am. And originally it was deployed so that vessels wouldn't run into each other. But now it's more or less used to track vessels. All vessels of a given size are legally required to project AIS. But sometimes the AIS is invisible, it's code channel interference, or there's some glitch, or when they're potentially doing things they don't want to be seen doing, it's turned off, okay? But as I said earlier, we can see all the other signals. We can see the vessel radar. So there's an illegal fishing one. The one in the middle is kind of interesting. We worked with the Republic of the Congo and Garamba National Park, and they felt they had some incursions into the park. Now, the only thing supposed to be in the park are rangers and animals. That's it, okay? So we flew over and we looked down and we were looking for mobile SATCOM, think Iridium satellite phones, Thuraya, Inmarsat, those kinds of things, and we got a couple hits. And the rangers went out and looked, and there were some campfires there. So where there's evidence, leading indicator that there's evidence of someone being in the park, whether it's a rebel or a poacher, they couldn't be sure, but it gave them a smaller search field to look for. I'll talk about one other one, the middle one and the bottom, GPS interference. Now, you may have read in the Wall Street Journal that even before the Ukraine invasion, we were picking up GPS interference as a leading indicator of troop movement. So as it turns out, if you've got a convoy of troops moving and you don't want a drone to come in and maybe engage you, you spew out GPS interference, and things that use GPS are interfered with that way. So anyway, it was extremely helpful for us to be able to do that and to track those movements. So we have a signals of interest catalog. What it means is that by now, we have honed in on specific signals that you can order up. You can say, for example, VHF push-to-talk marine radios. I'd like you to collect that over the Mediterranean Gulf. Or you could say, look at land radios over North America, or look at sat phones over the Ukraine. And on the left, you see a list of some of the existing signals that you could just dial up in our ordering system and order. And then on the right, what you see is that we're expanding our signal capability. The GPS interference you've heard about. UHF and VHF flex is the ability to pick a frequency anywhere in the UHF or anywhere in the VHF spectrum and say, collect 432 or collect frequency 500. And what we're doing is we're making it possible to do addressable collections anywhere up and down the spectrum. And there are other more sophisticated signals that we probably won't talk about here, but looking at the metadata of the signals that we collect in identifying what kind of emitter might that be. So I'm going to pass it off to my partner, Kate, at this time.
All right, thank you, Tim. So yeah, as you may have guessed from the title of the talk, so I know there's lots of different use cases for our data, but for this presentation, we're going to get deeper into specifically the illegal fishing use case. And what I want to talk about first is kind of set up how we typically try to detect illegal fishing today, what the workflow is, before I get into how we do that in AWS and how we're using our big data architecture to achieve it. And first to start, I want to emphasize there's a lot of challenges that are unique to the maritime domain. Cloud coverage is very frequent around like different ports of the ocean that can make other modalities like imagery difficult to get a good picture of the ships of the ocean. As Tim had mentioned, the AIS data, that's the voluntary position transmission that ships will emit, can be very noisy and messy. Sometimes it can be turned off altogether. It can be spoofed. So there's a lot of challenges with getting kind of clean data there, using that data source alone. Vast areas of interest. The ocean is large. This is a common issue with imagery platforms in particular. So we talk about electrical optical imagery and SAR. Their footprints of what they can collect is relatively small compared to what we can see with our RF satellites. And so whenever you're trying to scan large areas and trying to get a picture of that one ship in the ocean, and the ocean's quite large, it can be a real challenge without having additional data to bring in to find kind of the right areas to look in. And then the last piece is deploying patrols with confidence. So whenever there is nefarious activity happening in the ocean, there's usually limited resources on the Coast Guard and others who can take action. So you need to have a lot of confidence of where you're going to go, what they're doing, and making sure that you can intercept the illicit activity early in the cycle. And so building up that body of knowledge and that information that you need to be able to have confidence to take action is also very key in this particular domain. So to walk through kind of our general approach of how we detect this activity today, So we'll start with first doing the geolocations coming off of our satellites. So here we have a bunch of little cute ships in the ocean, and they're emitting their X-band radars. And so when our satellites passed over, we were able to capture that energy and then geolocate it onto the Earth. The next thing we'll often do is then layer in additional data sources. So the AIS data source, that voluntary transmission of who I am and where I'm going. So that information we'll take and look where those geolocations are and how close they are to the radars that we geolocated and see if they're close enough that we can say with some level of confidence that we think that this ship is this AIS signal that's being emitted. And so we'll do that, and we'll kind of pass through and try to associate as many of these vessels as we can. But what we'll find is that sometimes there are vessels where we cannot associate. So there is no AIS transmission. And that by itself, there's many reasons why that could be happening. It's not always nefarious activities, but it is kind of interest. It's interesting for us, and that's where you want to sort of focus in. So once we have here's a ship, it's a little red ship, we don't have any AIS near this vessel, we don't know who it is, we'll start bringing in additional data sources to do that analysis to try to figure out what they're doing and if they're engaged in illegal behavior. So we might look at things like historical vessel tracks. So where did the ship come from? Did it come from a port full of, I don't know, like pirates? I'm thinking like Pirates of the Caribbean, like they're all crazy. That could be suspicious, right? Additionally, if it's going to rendezvous with another ship and maybe we have an ID, so maybe we know that Bob has engaged in nefarious activity before and perhaps it's a sanctioned vessel, so Bob is a naughty vessel. Knowing that we're going to likely go rendezvous could also make this ship more suspicious as well. We can bring imagery sources if we have them, so bringing in EO, bringing in SAR if it's available to see if we can get a better kind of visual picture of what that ship may be doing. And then, of course, looking at what other vessels around that vessel are doing. If there's a known fishing area and there's lots of ships fishing nearby, and that's exactly where this unknown vessel is headed, again, that could indicate to us there's potentially nefarious activities. So we look at a lot of different data sources, bring those in, fuse them together to create this complete picture of what the ships are doing in the ocean and which ones may or may not be the bad actors. So as you can imagine, this is definitely a very big data problem. It's definitely a challenge for us. Bringing all these different data sources, some we own, some we don't, having lots of different teams within the company working on different parts, from building satellites to processing satellite data to doing analytics. So what I want to emphasize here in the next section is kind of our data lake structure that we built to help empower our teams to be able to discover data and build these analytics quickly so that we can make solving this challenge easier for our customers and analysts. To give an idea of kind of the scale when I say big data challenge, here's a quick slide kind of by the numbers. So we have over 100 million RF geolocations coming off of our satellites at HawkEye. There's over 350 million AIS messages being broadcast daily that we're trying to fuse with our geos and track those different vessels. Over 250,000 ships that are off in the ocean. Most of them are doing perfectly legal activities, so trying to find those few bad actors in that sea of many is a challenge. But illegal fishing by itself is also a very big, issue, right? There's $23 billion estimated that's getting lost to the illegal fishing industry every single year. And illegal fishing represents the 20% of the world's catch. So huge impact on our ecosystems as well as the economic impacts as well. So it's a big issue to solve, but it's a challenging one, right? How do we find those few kind of bad actors in the sea of data that we have? Okay, so this is our architecture for our data lake. And our data lake is all about how we bring those many data sources together to empower our teams to be able to build analytics to make it easier, again, to find those few bad actors in that sea of many. And there's a lot on here, and I'm going to do my best to make sure we have time for Q&A so you can come back to this slide and go deeper on different services. But I do want to walk through kind of the big points here on why this architecture works for us. So we have a bunch of different teams within the company, a bunch of different development teams. As I mentioned earlier, we have like our space teams who work on the space processing. So they're responsible for taking the raw data and then creating those geolocations and building all the algorithms that do that. We have teams that are focused on kind of user delivery and applications. So they're working to get data to our customers, but also to build tools to help our analysts be able to interact with our data better. We also have our data science groups, which are building those machine learning algorithms and different complex analytics. So all these different teams are working with data. They're all generating their own data sets. They're using each other's data. And so this design, when you look at the producer layer, the green one at the very bottom, allows those different teams to publish their data as they create it into our central data catalog. So processing group is building new, like UHF, VHF Flex algorithms, and they're creating these really cool data sets coming out of that. They can now publish that into their data catalog, which flows up to the yellow layer, which is the central data catalog layer. So that's being powered by lake formation. So we have one big central data catalog where someone like the data science team could discover that processing now has new geolocation types coming in there. I can find those, I can pull those into my group, and now I can start doing some analytics against those and seeing how it works with our existing algorithms as well. So that central data catalog is super key, being able to discover all the different data sets being generated by the teams. Another big thing about this design is that we wanted to make sure that it was modular so that the teams can move at the pace they want to. So space team can publish data sets when they think it's ready. Data science can consume those whenever they want to as well. It's very decoupled. So all the different groups are working at their pace with their roadmaps and their speed, but we're able to share information freely between those different groups. And lake formation as this kind of central layer was super key here, because as you can imagine, this gets pretty complicated pretty fast, right? Lots of different access control and permissions and auditing. We want to know who's accessing what. And so that's all baked into the lake formation service that makes that much easier for us. It would be really hard to scale this without that particular layer in the middle of this data lake. And then up top, we have our consumer layer. So this is where we can pull data out. So whenever I discover different elements within the data lake that I want to leverage and use, I can very easily request that data through the data catalog, pull it into my accounts, do machine learning against it, do what we want to do. And then if we do create a new data set, guess what? We could publish that back into the data lake too. So you can see how it becomes a very scalable kind of design. And what's cool is that once we found that being able to discover data was much easier, we were able to start doing some more interesting analytics because we could go from the raw data coming off the spacecraft to everything in between that goes into creating that final geolocation, and then also looking at our third-party data sets that we bring in to do the fusion. So we could do queries that could go through all this information, pull it together, and pull it down, which really empowered us with our analytics to be able to really build more interesting machine learning models. Because before, this would be in different silos, right? Different groups would have products living in their accounts in AWS, and they would be working against those. And on the data science team, unless we knew that particular engineer working on that particular data set, it could be hard to find, right? We might not know that that's even an option for us to bring into our algorithms as a feature. So the data discovery piece was absolutely critical to be able to accelerate our analytics piece. And ultimately, the analytics are critical. That's really one of the big things that the data science team is here for, is being able to take these dots on the map and provide that context around them. The example I gave at the very beginning with the ships in the ocean, right? The ships being detected in the ocean is interesting, but it's once you start layering in those many data sources and tying them together that you start to understand the context around why this vessel may be engaged in activities that we would be interested in. So we're looking to exploit these data patterns and build analytics that help us find these complex patterns to be able to add that context to our data. So I want to call out one model in particular that was enabled by all those different data discovery elements that I think was very, very cool. So we went back to that example. We had Bob, and we were able to get that association through the AIS to the X-band radar. And that's how we knew that this radar is Bob's radar. Betty, another example of that. But each radar has bits of it that are a little unique, is what we had found. When we looked at tracing back from that final geolocation to the raw data, we were able to actually build machine learning algorithms that could detect Bob in the future based off of the waveform alone. So the idea is that in the future, if we were to see just that X-band radar, because we saw it before, because we tied it to Bob previously, we can now map that in the future again. So this becomes a really powerful tool whenever we think about that red vessel where we didn't have AIS nearby, we just had the X-band radar geolocation. If we had seen at any point that particular radar before and did have a tie back to AIS, we would be able to identify it again using the waveform. And so unlocking these kinds of insights, using the power of machine learning, but also being able to discover the data was really fundamental to being able to develop these types of algorithms for our customers. And we saw a real acceleration within the data science team as we were able to get access to more data. Imagine that. Data scientists love data. So the unique signal recognition was definitely one core component to the work that we've been doing. But we also were able to do things like opportunity regions, which is the orange kind of blob you see off on the side, which is looking at when a vessel, if we have 2 points of a vessel and we have unknown data in between, and that could be because it was, I don't know, an hour before we saw it again, so we only saw 2 data points and we want to know where it went, or we weren't looking. Opportunity regions predicts a path between those 2 points. It looks at a bunch of different factors like the ocean, land, the distance between them, other vessels nearby, that allows our analysts to explore potential rendezvous or other activities that it could have engaged in during those periods of time. There might be gaps in the data collection. We also built models for object recognition for both EO and SAR data, so that whenever you bring in those extra data layers with imagery, we can do object detection to detect the maritime vessels, but then we can do the correlation and say we think that these vessels are tied with these geolocations because we know where the vessels are through the computer vision algorithms. So we had a lot of different models that we were able to build and accelerated timeline because of our ability to find the different data sets that we needed. But I also want to call out that while the machine learning part is super cool, there's also a lot of power in just being able to do more complex queries and being able to do more complex joins across the data that you already have. So being able to say, once I found this vessel, let's say I used the cool unique signal recognition algorithm, and now I know that this unidentified vessel is likely, I don't know, Frank, and we saw Frank a few months back, and we had an AIS tied to it, so now we see the same radar. But we can go ahead and do queries. So now we have Frank. Let's see, Frank was owned by this company here, and Frank has rendezvoused with these vessels here. But those are all just data queries, and that by itself has a lot of weight and power. So being able to just do these complex queries across many data sets by itself has been really critical to understanding that context or what we're seeing in our data. So I want to leave time for Q&A, but before we switch over to the questions, I do want to land with kind of one story, the example of the results that we've been able to achieve through these new algorithms. And this example here is a picture of the Galapagos EEZ, Economic Exclusion Zone, and that's the blue blob in the middle there. So you're not allowed to fish inside of that circle. That is an economic exclusion, EEZ, cannot go in there. The yellow you see kind of on the bottom there, that is AIS. So you see there's a bunch of different ships right along the border of the EEZ, but they're not inside of it. So it looks like they're all playing by the rules and respecting the boundary. But we got reports through open source indicating that there was potentially some illegal fishing happening within the EEZ. When you look at AIS alone, it looks like nothing's there. So we took a look at our RF data coming off the HawkEye satellites, and we geolocated a collection of X-band radars, those are maritime radars, within the EEZ. So we did see indicators that there is activity happening within this zone, even if the AIS isn't reporting it to be there. So knowing that there are radars inside of this EEZ, that's interesting, but it's not enough to know that illegal fishing is happening and be able to validate that. So kind of the next thing to do is take a look at those radars and start figuring out who's who. Whose radars these belong to, where have these vessels been, and start trying to do that analysis to see if potentially there are some bad actors. And so we just did just that. So these little orange circles, you can see the few in there, those are the X-band radars I was talking about. And so this one here, we got a hit. So while it was within the EEZ, it didn't have any AIS associated with it at the time. Whenever we looked at previous detections of that particular radar, we found that this one is most likely coming from a Japanese vehicle carrier. It's shipping cars, basically, so it's unlikely that that particular vessel would be doing illegal fishing. So we'll look and see what else is in there. That one's probably not the ship we were looking for, right? The next one that we got a hit on was an Ecuadorian tanker. The Galapagos EEZ belongs to Ecuador, so the fact there's an Ecuadorian vessel traveling through here, again, by itself, not too suspicious. It's probably just traversing its regular path. So probably not going to be engaged in any kind of illicit fishing activity. But the third hit that we got, this one was interesting. So this cargo ship, the Woohoo that we got a hit on, whenever we did the data queries, we found that it had actually changed, I guess, hands and been purchased a few times, and some of the other companies that it had been involved with, they do have some track records of potentially doing nefarious things. So while it's not necessarily the smoking gun, we don't know for sure that this vessel is engaged in any kind of illegal fishing. It is odd that it would be in there. And so this is where we might want to spend our time. So we were able to really quickly drill in on the evidence that we need to start doing further analysis, bringing in those more data sources, and determining if this vessel is part of a larger fleet that could be engaged in illegal activity. So this is, again, the power of having that RF-first approach. So being able to see the X-band radars within the EEZ from our satellites was key, but then also having these analytics that help you then get the insights around those data points to be able to make more decisions. So with that, before I turn it over to Q&A, I just want to hit kind of the high points and go back over a few things. So the first one is that our data lake, so we're using a data mesh architecture. And we found that that's really helped us empower our individual teams. As I mentioned, the software development happens across multiple groups within our company. So having the ability to publish data when you feel it's ready on your team, being able to consume that data across without having to contact every database owner, every data storage owner, helped us all move at a much faster velocity and scale as well. So those are really key to our design. And the data lake itself, the data discovery component, has really helped us accelerate our analytics development. So being able to find data sets that are being generated within the company by different teams very easily, being able to test those very quickly to see if perhaps those features improve our models, was able to accelerate our analytics development and build some really cool machine learning models. Lake formation, though, is super key. Data mesh design is a little bit more complicated than just having one central data store. So you need to have that layer in there that's going to help with all the auditing and permissions and all the access control type stuff, because it can be, I don't know how you'd really be able to scale very confidently otherwise. So that's definitely a key component within our design. And then on the example that I just gave, space-based, RF remote sensing is definitely one of those early indicators of activities. It gives us a lot of additional information that you wouldn't have to be able to gather with AIS data alone. And whenever we look at the RF waveforms itself, we can also start to extract information about the specific vessels that we can then use to basically find more interesting patterns within their behavior that could alert us to activity. And so data fusion is super key, and that's where the data lake definitely helps us come in, because we can do queries across many data sets, pull it together, build cool models, and it's all good. So with that, I want to make sure we have time for questions. So I thank everybody for attending, and we'll open the floor.